Let's go through and look at putting all this together. Give me 1 second here. I want to make sure, nope, that's not showing the thing that it needs to. Give me 1 second. There we go. Alright, so let's look at this in our larger picture. We've been dividing and talking about factors. And in the remainder theorem, I pointed out the use of the remainder theorem and where all of this going leads us to what we're going to call the factor theorem. That a polynomial has a factor if and only if the remainder is 0. And so notice, this really uses our remainder theorem. So our remainder theorem said the remainder of f of x divided by x minus k is equal to f of k. And so the factor theorem says, hey, if the remainder is 0, x minus k was a factor. Because our factors do not leave remainders. And so this system sets us up so that we have, we can find factors by finding areas where the remainder is 0. And what this ends up doing is, if you look at a graph of a function, you can find all the factors. So if we look at this graph here, it crosses the x-axis, or the function has a value of 0 at -1 and +3. So these are factors. And so what that looks like, let me move over here to the blackboard. Scroll down a bit. These places where our graph crosses, the graph crosses the x-axis, are x-intercepts, roots, solutions, zeros. They're all words that we're going to have to end up using interchangeably. For right now, the word 0 kind of makes sense, because when you're on the x-axis, right, when you're here on the x-axis, the value of the function at those points is equal to 0, because your y value is at the 0. So our remainders are the place where the function equals 0, or I'm sorry, our factors are the place where the remainder is 0. The remainder is 0 when the function equals 0 at that point. I'll make that a specific point. And so all these things end up meaning the same thing. So in the example, that was -1, 0, and that was 3, 0. That means whatever f of x is, it has the factors of x. Well, let's write these out in one more step. So if this is a factor, this means x at this point is equal to -1, and x at this point is equal to 3. I'm going to put everything to one side, so I add 1 to each side. I subtract 3 from each side, and there's my factors. Remember, a times b equals 0. So if f of x equals 0, then f of x can equal a times b if, and this is true, if a equals 0 or b equals 0. Well, there's my a equals 0 and b equals 0. So I can rewrite my function as these factors. That's what the remainder theorem is telling us, is where these things cross the axis, those are solutions for x, right? We recognize these as solutions for our variable x. Well, if I solve this and I get everything to one side for 0, this part is the factor. And so we now have a way of describing our polynomials based on where they cross the x-axis. The thing is, there are an infinite number, because I can put an a out in front of this, there are an infinite number of answers to this, depending on where the rest of the function goes through. And so what we tend to do is we'll throw a constant a out front, and we'll need some other point, like the vertex or a piece of data up here that we solve for a. And so this is the thing that we're going to have to watch for, is we can have the same solutions to multiple polynomials. They will have the same form, but there can be a number in the front that multiplies them out, multiplies them through. I think that, this has a lot of meaning for us, for how we find these things. Because if I look at multiplying this, right, I'm just going to multiply what's in the parentheses. I'm going to leave a hanging out front here. So I get x squared minus 2x minus 3. Now a would multiply through everything here. So the thing that's really telling me where the factors could be is this last number divided by a. Right, I get ax squared minus 2x minus 3a. And so the part that's going to hold all of our clues for us are going to be the leading coefficient and the trailing constant. The stuff in the middle matters. It tells us where it turns, it tells us what it does, but it doesn't help us find anything. The end points will be our clue, because no matter my roots, my solutions, I can see clearly the beginning and end points. So that's something we're going to keep building towards, is that this leading coefficient and this constant. So remember back, 2-3 lectures ago, when I was talking about the polynomials and said, what's the leading coefficient? What's the constant? Well, it's because they're going to hold a lot of information for us. Sorry, that's 2 times a also. And they're going to point back to what the roots are, because if I can pull that a out, I'm going to find the roots. Every time I say that, I think of Questlove. Alright, so let's look at some more things that we can look at from how these intercepts work and what a polynomial is. And so what we're going to do is we're going to talk about factored forms. And so we're going to go into the abstract, and then we'll pull some specific examples out of it. So if I have a polynomial, and I'm going to do it in that lovely general form. So I can have any degree of n, and I can have any arbitrary coefficients. Well, it's going to it has n real zeros. And so we're going to, and again, I'll use the other words, roots, solutions, but it's going to have n of them. So we can write those using C. I don't know why mathematicians, they like C for the roots. So there's going to be C1, C2, C3, and so on, up to C sub n. Those are all the possible solutions. So this matches this, the degree. then we can write it in a completely factored form. A completely factored form. This is what I was trying to pull out. And so I can pull out the a sub n. And then I'm going to have x minus c sub 1 times x minus c sub 2 times x minus c sub 3 times dot 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 x minus c sub n. And so all of these solutions come out factored. So notice the leading coefficient can be pulled out. And when I multiply all of these together, the last terms combine to give me the a sub 0. So that's the importance of the leading coefficient and the last term. They can combine together to find it. Now, sometimes really neat things happen. Sometimes, and I'm going to use a specific example, you can have a polynomial where the factor is repeated. And this repetition of a factor has meanings. And so, well, I'm multiplying the same thing 3 times. So I would take it to the 3rd power. Well, we're going to come up with another term for this idea of repetition. And we're going to be able to call it multiplicity. The repetition of a zero-root or solution talks about its multiplicity. And that actually talks about how the graph is going to act once it gets near the x-axis. So prelude, and we'll get into this, is this function overall is going to be to the 3rd power. It's odd, and it crosses at 2, right? Because that root is 2. And because this goes 3 times here, it actually punches through at 2. Now if I had a function, let's say I'll just do it like this, that has a multiplicity of 2 at x minus 2. It's going to hit here for the -1 and over here for the 2. Now this is an odd function still. It has the same overall power. So I'm going to be starting down here. I'm going to need to turn here, but I have to end going away because it's an odd power. Odd powers start on one infinity, end on the other infinity. And this has to cross at the roots. But if the multiplicity is even, it bounces. And so this idea of how often it's repeated will tell us a lot about the behavior of the function. So here, I had an odd repetition. I have an overall odd function. It has to start at one infinity and end at the other. When I get to this crossing point, I have to punch through. Here, I still have an odd function because the overall power is 3. Right? This x times this x squared will make it x cubed. I have to start at negative infinity and end at positive infinity. I punch through the -1. Somewhere I have to turn to get to the positive 2. But because I have to go off towards negative infinity, I have to turn back up. And the multiplicity shows that. The multiplicity of a solution shows that. And so these things start building up nicely for us, and we can get things out of the graph. All right, so we're getting our idea here is that we have these functions. These functions allow us to build different parts of this out, and based off of their roots. And those roots correspond with our function becoming to the degree, crossing the x-axis, coming to or crossing the x-axis. And so we have our multiplicity, we have our factored form. Let's look at finding some graphically for us here. So I'm going to get a graph up in Desmos. Give me a second here, and we'll pull it apart. So let me switch over to Desmos. And the graph I'm going to look at is 2x cubed minus 4x squared. So I'm going to come in here. F of x is equal to 2x cubed minus 4x squared. Whoops. Make sure I have to jump 2 screens here. Minus 4x squared minus 10x plus 12. Minus 10x plus 12. So minus 10x plus 12. And here's my function. I'm going to zoom out just a little bit so I can see the turning points on this. But what we want to notice is, hey, I've got roots. I've got places where I have roots. And I'm going to click them on Desmos here, because they're going to tell me the values. They're the places where the y value is 0. And they give me the x value for the roots at this point. So I have x of negative 2, x of 1, and x of 3 are the roots for this function. So what was my function here? I had f of x equals 2x cubed minus 4x squared minus 10x plus 12, and my roots were x equals negative 1, x equals 2, and x equals 3. No, that's not. Let me look at this graph. Sorry, I'm looking at 2 different things. My roots are negative 2, 1, and 3. Get my signs right on this. Alright, so I'm going to pull back over to the blackboard here. So we're finding the negative 2, the 1, and the 3. So this is what this looks like. This function has these roots. Using this graphical utility, where I cross the x-axis, I was able to find the factors of this. Now note, my leading coefficient here is 2. So using my completed factor formula, which I'll write here in yellow, it said that I can write a function as a sub n, the leading coefficient, times x minus c1 times x minus c2 times ... x minus c sub n. Well, I have a 3rd degree polynomial, I have 3 linear factors, and I have my a sub n. So I can write this in completed factor form as, well, let's solve this. So I'm going to solve these into factors. So I'm going to subtract 1 from each side. X minus 1 equals 0. I'm going to add 2 to each side here. X plus 2 equals 0. And I'm going to subtract 3 from each side here. X minus 3 equals 0. And now I have factors. Well, those factors look like these, right? Here's x minus c1, x minus c2, minus a minus is positive, x minus c3. So I can bring my 2 out front, and I can write my linear factors. And these are equivalent. What's nice about this is telling us exactly where the function equals 0, which helps us solve problems. So what would be really, really nice is, let's take this problem here. And let's say we knew a solution. We knew one solution. Let's say we knew x minus 3. So we're going to look at this and we say, hey, I know x minus 3 is one of the factors. So I should be able to test this by using the remainder theorem and division. In both cases, we'll get division. So we're going to say x minus 3 is one of the factors. Let's test it with the remainder theorem. So the remainder theorem tells me if I am testing this factor, f of 3 should, if I'm going to test it, I want to check to see if f of 3 does it equal 0. And so f of 3 is going to be 2 times 3 cubed minus 4 times 3 squared minus 10 times 3 plus 12. So 3 cubed is 8, so that's 16. I have a calculator here, I should run to the calculator. Whoops, and no, 3 cubed is not 8. 3 cubed is 27. So this is 54. See, I should run to the calculator. In fact, before going on, I'll just grab my calculator. So 2 times 3 cubed minus 4 times 3 squared minus 10 times 3 plus 12 equals 0. Minus 3, 6, and 8 equals 0. And so we know this is a factor. So if I knew this one factor, I could check it this way. Well, look what else we can do with it. I'm going to continue to use this number, knowing the factors from the graph. I'm going to show some of the other things we can do with it. So let's say I had a cubic and I knew one of my solutions was 3. Well, I could use synthetic division. So I'm going to use synthetic division down here. My coefficients were, I'll change my colors again, 2, negative 4, negative 10, and 12. And I'm using 3. Bring my 2 down. 3 times 2 is 6. 6 and negative 4 is 2. 3 times 2 is 6 again. 6 and negative 10 is negative 4. 3 times negative 4 is negative 12. Remainder of 0. I know this is a factor because I have a remainder of 0, but look what else I found out here. I found that x minus 3 times 2x squared plus 2x minus 4 is the same thing. You're like, oh, okay, well, how does that help? What can we do with this? Well, this is quadratic. And I know how to factor quadratics, right? In fact, I can pull out the 2. And then I have to find factors of 4 that add up to positive 1. 1 has to be negative and 1 has to be positive. Did I miss something here? Oh yeah, when I pulled out a 2, this has to be a 2. My bad. pulled out the 2, this becomes 1, 1, and negative 2. Well, I have factored quadratics, x minus 3, factors of negative 2 that add up to positive 1, and I found all my roots. So this idea of being able to break polynomials up into their factors, this combination of using division and using the remainder theorem can help us find one root. Once we have one root, we can start breaking our polynomial down. So let's look at what we did here. Now we started with this graphically. We had this function, and we be back with you in a second here. Sorry about that. Had a bit of a drop there. You guys okay? All right, so I end up in Desmos. And let me get back into Desmos here. Sorry, I lost connection for a second there. We graphed this solution. We were able to find all the roots. And we're able to express this in terms of its factors. And factors equal roots. Roots equal solutions. And we'll pull out more of that meaning as we go through. Well, if we knew one of the roots, let's say it was a problem we had that we knew was a polynomial, and we knew one of our solutions somewhere in all of this, 3 was a number that popped out, we could check that by using our remainder theorem. And guess where we're going? We're going to find ways that we can figure out what possible roots are. The keyword is possible. All right, so we put 3 in. Hey, it is a factor. Well, knowing it's a factor, I divide by it. So I use synthetic division, dividing by that possible root. And it takes my third order polynomial and breaks it into one linear term, which I knew was there because of my remainder theorem, and a second order quadratic. But we've worked with quadratics. And so the work we've done with quadratics lets us jump this last step. Let's just say, well, I can factor a quadratic. I can find the roots or the solutions to the quadratic. I have the quadratic formula. So this deconstruction is going to be our game. We have these higher order polynomials. We have these nth degree polynomial terms, and we need to break them down into lower and lower terms. And those lower and lower terms, we need to break down again and again until we get linear answers or imaginary answers. That's good. All right. So this is where we're at here. I posted part of today's lecture, which is the graphing of Desmos, focusing on sections 4.1 and 4.2 with Desmos, separately. What you should do is in the playlist, go watch the graphing with Desmos. And we're going to look specifically in the graphing with Desmos stuff at what multiple roots do. The homework posted up is for sections 4.1 through 4.2, or for 4.3. I'm going to be posting the stuff for 4.4 this week. Again, the due dates are out a bit. Watch the videos and go back through. Please keep emailing me your questions. Those questions are turning into example videos, and the example videos are either entering the lecture directly or being posted up as separate little lecture material. So what I would do on the back half of this lecture is go through the what will be a total of 5 videos on using Desmos for the graph. If you want to use a different graphing utility, like you want to use your graphing calculator, all of this information is the same. You're grabbing this from your graphing calculator. You just use a different utility to find the points. And if you have a question on your graphing calculator or the graphing program you use, email it to me. I will try to do some demos with that. I have ordered a better camera than my webcam so that I can video the calculators I use so you can see them. I do not have a calculator interface or emulator. I'm looking for one of those also for some way to do that, but I can break down the videos for the main graphing calculators, the TI series. If we're outside of that, we can figure it out. That's what we're here for. That's all I have for today. It was a short hour today, but this is actually really hefty material. This is stuff you have to start playing with, breaking these things down into roots and rebuilding them back up. And I'm going to want you to go through those Desmos videos, and I will point those out in my T-Day email. All right. Luckily, we didn't get... this is odd. Okay. I noticed tons of people in, tons of people out. Looks like the connection dropped a little bit. This seems to happen on Tuesdays. I'll go back and review this and re-record anything that's missing in it and post that up. My apologies for that. I saw the connection drop and I re-added it. I was about to say, at least we didn't get mauled by any stalkers or crazy internet trolls this time around, but we might have had the attempt and I lost the connection in the middle of it there. So I'm gonna, right after this, go back, review this, and anything that's missing in the lecture I will add up as a second video with the Desmos material.